Every year, humanity manufactures more transistors than there are stars in the observable universe. Your phone alone contains tens of billions of them. But every single one of those transistors begins its life in the same place, on a polished disk of silicon so perfect that a single speck of dust can destroy months of work. Because the modern world doesn't just run on electricity, it runs on crystal. Today, virtually every processor, every memory chip, every sensor on Earth is built on ultra-pure silicon wafers. Not exotic metals, not rare compounds, silicon. The second most common element in the Earth's crust, refined to a level of purity that borders on the impossible. Across the globe, entire industries, financial systems, and military networks depend on these thin gray disks manufactured with atomic precision inside some of the most extreme industrial facilities ever built. And this is where the real process begins. The entire system starts with something deceptively simple: quartz rock. Ordinary silica, the same material found in beach sand. But raw quartz is nowhere near pure enough to carry electrical signals through circuits measured in nanometers. Inside massive arc furnaces, the quartz is combined with carbon and heated beyond 3,000 degrees Fahrenheit. At these temperatures, oxygen is stripped away from the silica, leaving behind molten metallurgical grade silicon. This first product is roughly 98% pure, and in almost any other industry, that would be more than enough. In semiconductor manufacturing, it is nowhere close, because in chip production, purity is everything. Electronic-grade silicon must reach a purity of 99.9999999%. That's 9 nines. To put that in perspective, it means fewer than 1 foreign atom for every billion atoms of silicon. If a truckload of sugar were refined to that standard, the total contamination would amount to a single grain. To achieve this, the metallurgical silicon is converted into a liquid chemical called trichlorosilane and distilled again and again, separating out trace metals like iron, aluminum, and boron. Then, inside sealed reactors, the purified gas is deposited back into solid form, growing thick rods of polysilicon atom by atom. But even this ultra-pure material has a fatal flaw. Its atoms are arranged in the random, disordered grains, and electrons hate disorder. Every boundary between grains scatters electrical current and creates defects where transistors would simply fail. What the industry needs is not just pure silicon. It needs a single, flawless crystal. And this is where one of the most remarkable processes in modern manufacturing takes over. The purified silicon is loaded into a quartz crucible and melted at more than 2,500 degrees Fahrenheit. Then, engineers lower a small seed crystal, a perfect fragment of silicon, until it barely touches the surface of the molten pool. Slowly, the seed is pulled upward while rotating, and something extraordinary happens. The liquid silicon freezes onto the seed, copying its atomic structure layer by layer. Atom by atom, the crystal grows downward into the melt, forming a massive single crystal called an ingot. This is the Czochralski process, and it demands almost superhuman stability. The pull rate is measured in fractions of an inch per hour. Temperature gradients are controlled to within a degree. Even subtle vibrations in the building can disturb the crystal lattice. Over the course of several days, the ingot grows into a gleaming cylinder up to 12 inches in diameter and more than 6 feet long, weighing hundreds of pounds. One continuous, unbroken crystal. Billions of trillions of atoms, all locked into a single perfect arrangement. Now the transformation continues. The ingot is ground to an exact diameter, and then it meets the wire saw. Hundreds of parallel strands of ultra-thin diamond-coated wire slice through the crystal simultaneously, cutting the entire ingot into hundreds of wafers in a single operation. Each wafer emerges less than a millimeter thick. But at this stage, the surfaces are still rough, scarred at the microscopic level by the cutting process. And for semiconductors, rough is unacceptable. The wafers are lapped, chemically etched, and then polished in a process called chemical-mechanical planarization, a combination of corrosive slurry and precision pressure that smooths the surface down to the atomic scale. The finished wafer is flatter, relative to its size, than almost any object humans have ever made. If a 300mm wafer were scaled up to the size of the United States, the tallest bump on its surface would stand just a few inches high. But production is only half the battle, because everything that happens next takes place in an environment more sterile than an operating room. Semiconductor fabs maintain clean rooms thousands of times cleaner than a hospital surgical suite. The air is completely replaced multiple times every minute, filtered down to particles a fraction of a micron across. Workers wear full-body suits, not to protect themselves from the wafers, but to protect the wafers from them. A single human being sheds tens of thousands of skin particles every minute. And in this world, a particle is a weapon. Modern transistors are smaller than most viruses. A dust particle landing on a wafer isn't a blemish. It's a boulder crushing a city block. One invisible speck can destroy an entire chip, and the value of a fully processed wafer can reach tens of thousands of dollars. Before any wafer enters production, it must pass relentless inspection. Laser scanning systems sweep across the surface, detecting particles and crystal defects far too small for any microscope operated by human eyes. Flatness is verified in nanometers. Electrical properties are measured point by point across the entire disk. If the crystal structure shows dislocations, if the surface shows contamination, if the resistivity drifts outside specification, the wafer is rejected. Because a defect at this stage doesn't cause one failure. It multiplies. A single wafer can hold hundreds of individual chips, and every flaw silently kills the devices built on top of it, sometimes without being detected until months later. The wafers that survive are sealed inside ultra-clean cassettes, purged with nitrogen, and shipped to fabrication plants around the world. And there, the real magic begins. Layer by layer, through hundreds of steps of deposition, lithography, and etching, engineers build entire cities of circuitry onto that polished surface. The most advanced machines on Earth project patterns using extreme ultraviolet light, with a wavelength of just 13.5 nanometers, printing features so small that a few hundred of them could fit across a single red blood cell. None of it works without the wafer beneath. Every transistor, every circuit, every processor inherits its foundation from that one flawless crystal grown in a furnace weeks earlier. And the stakes could not be higher. The global economy has learned, painfully, what happens when this supply chain stumbles. A drought at a major fab, a fire at a single materials plant, a shortage of production capacity, and within months, car factories shut down, electronics prices spike, and entire industries grind to a halt. Because there is no substitute, no alternative material, no backup process, no shortcut that delivers what a perfect silicon crystal delivers. Every message you send, every photo you take, every calculation performed by every computer on Earth begins on a gray disk of crystal engineered at atomic precision. From quartz rock to furnaces hotter than lava, to a single crystal pulled from molten silicon, one atomic layer at a time. The silicon wafer has quietly become the foundation of the modern world, and it all depends on a surface so perfect that a single invisible particle can bring it down. If you want to understand how other critical systems survive under the same level of pressure, you'll find more videos on this channel. Like this video if it helped you see what normally remains invisible, and subscribe to keep discovering how the systems that run the world truly work.